Section 7 is on continuity and the intermediate value theorem. All right, so we talked about the intermediate value theorem in pre-calc. I don't know if you guys remember, but continuity is something that's new. So it says, for some functions, you've found that it's very easy to compute the limit as x goes to a. You can simply plug in the value. So if it said compute the limit as x goes to 2, some of them you can just plug in 2, right? So functions that have this property are called continuous at a. So the definition of continuous, this is important. So anytime the AP test says something about a continuous function, you need to remember this. So it basically says that if I have a curve and I'm going towards a certain x value, I want this to be a filled-in point. Okay, so our limit, as we approach from both the left and the right, go to the same number as f of a. That's all it is. So your limit is equal to the filled-in point. Okay, so really, the easy definition for continuous is that you can draw the curve without lifting your pencil. So do you guys see how the only way you could draw a curve without lifting your pencil is if it doesn't have a hole in it? We can't draw that curve. We would have to skip over the hole. Okay, so we need for there not to be a hole. We also can't have like a vertical asymptote, anything strange like that. So it says for this to be true, you really need for 3 things to be true. So these are all 3 conditions for continuous. So you need f of a to be defined. So there needs to be a point there. You need the limit as x goes to a of f of x to exist. And then the third thing is the definition. You need for them to be the same thing. All right. So using the graph of f below, at which numbers is f discontinuous? So where is it not continuous? Where would you have to pick up your pencil in order to draw it? Yes, what do you think?
At x equals 0.
At x equals 0, it's discontinuous, right? So right here, because you'd have to lift your pencil. 6. What about x equals negative 6? Yep, any others?
X equals 5.
Yep, x equals 5. Easy enough, that's where it's discontinuous. So it says why. So x equals 0 is what we call a jump discontinuity, because it jumps from one point to another. X equals negative 6 is also a jump, because we jump from one y value to another y value. And what do you think x equals 5 is called? A hole. Okay, the fancy calculus term is removable. And I'll talk about why that's called a removable discontinuity. So it says, where are each of the following functions discontinuous? Okay, so we have x squared minus x minus 2 all over x plus 1, and it does factor. It factors into x minus 2 times x plus 1 all over x plus 1, and we know it cancels. But we know that when we cancel something like that, that there's a hole there, right? So there's a hole at x equals negative 1, so it's discontinuous at that point, so at x equals negative 1. And it's continuous everywhere else. There were no vertical asymptotes. There was nothing else. It was just that hole. Yes?
But it's called removable because in the equation you can remove it.
You can remove it by filling it in, right? You can remove the discontinuity. Yeah, so basically what he's saying is this graph, if you sketch it out, it looks like this, but there's a hole at x value of negative 1, so right here. So we can make our function continuous if we chose a point to fill that in. So do you guys see how we could say, oh, well, I'm going to choose the point at negative 1 to be negative 1 comma negative 3, and then it fills in that point. So we can remove the discontinuity.
Can you just do that?
No, we would have to make it a piecewise function in order to do that. All right, so B, so it says f of x equals 1 over x squared. Do you guys remember what 1 over x squared looks like? It's a very important thing in calculus, like this, right? So it says it looks like this, except at 2, or at x equals 0, we have the point 2. So it looks like that. So is it continuous? Can you draw it without lifting your pencil? No, you cannot. So it's discontinuous. Discontinuous. I know. At x equals 0. You can write not continuous. It's just as long.
At x does not equal 0, you mean?
At x equals 0. It's discontinuous at x equals 0. Or not continuous at x equals 0. All right, so here we go. So this one.
You can't draw these two things without lifting your pencil.
I know you can't draw them, so you have to skip over 0, right?
It says if x does not equal 0.
So we say it's discontinuous. It's not continuous at x equals 0. All right, so here we go. So we're going to factor. So I have x minus 4 all over x minus 4 times x plus 1. So we know that there's a hole there. So if I was sketching this out, I would have the graph of 1 over x plus 1. Do you guys all know what that looks like? It looks like 1 over x, except it's been shifted in what direction? Left 1, the vertical asymptote is at -1. So otherwise it looks like this. But we know that there's a hole at 4. All right, so the question is, does this other part of the piecewise function, does it fill in the hole? So it says we have 1/5 if x is equal to 4. So, you know, is it here? Is it here? Is it here? We don't know. How can we find it? Yeah, if you plug in x equals 4 into the simplified version, we would get 4, 1/5 as the whole, right? So is that the point? Yeah. So really this piecewise function, there was no point to writing it as a piecewise function. It's really equivalent to 1 over x plus 1. It's the same function as 1 over x plus 1. Okay? So that filled it in. So then it would just be discontinuous at what x value? -1, yeah. Because of the vertical asymptote. That's where you're lifting your pencil. You do not have an x value of -1. All right, do you guys remember the greatest integer function? It's been a while. All right, so the greatest integer function is the greatest integer that's less than or equal to a certain value. So if I had like 2.3, the greatest integer that's less than or equal to 2.3 is 2. If I had 3.1, it's 3. 3.01, it's still 3. Right, but once I get up to 4, the greatest integer less than or equal to 4 is 4. So the way that this is drawn is like little stair steps. So if I was at 1, the greatest integer less than or equal to 1 is itself 1. So actually it's other way, isn't it? Open. Is that what you're going to say, Grant?
I had my hand up. and
You did. I'll give you the point. Now I'm confusing myself on how I'm drawing it. The greatest integer less than or equal to 1 is itself 1. So they're filled in on the left, open on the right. So they're like this. Got a big list going on again today. All right, so where would it not be continuous? So it's discontinuous at what values? Not everything, because at 1.2 it's continuous. At every integer, right? So it's discontinuous for all integers. And those are the jump discontinuities, right? All right, so the first thing is the removable discontinuity. So that's the fancy way of saying that it's a hole. So the discontinuity is removable at x equals c if we can define f of c to fill in the hole. That's like that piecewise function that we did in part C. So if we said, okay, well, we have this original function, the x minus 4 over x squared minus 3x minus 4. How can we define another part to it so that it fills in the hole? Well, you could make that point 1/5 if x is equal to 4, right? So it would fill in the hole. So it removes the discontinuity. We call the value c that fills in the hole the continuous extension. Fancy.
What happens if you can't fill in the hole?
If you can't fill in the hole, then it's not a removable discontinuity, right? So it wouldn't be a hole then. So if you had like a vertical asymptote, for example, like there's nothing that you're going to fill in to make that continuous. So that's not a removable one. So the other ones are called jump discontinuity. So that's when your left hand and right hand limits go to different y values. So you have to jump from one place to another place. And then the infinite discontinuity is at a vertical asymptote. So that's where you go to infinity or negative infinity. Yes?
Does that not work for horizontal asymptote?
It does not work for a horizontal asymptote because it's actually, there's a x value defined for that. Like for every horizontal asymptote, like if we go this way, see how we have all the x values here. Okay, there's nothing where we're jumping over an x value, like a vertical asymptote. We have jumped over something to get that, okay? All right. So it says, just like when we learned about left and right-hand limits, we can have things that are continuous from the left and continuous from the right. So continuous from the right just says that the limit as x goes to a certain a value from the right of f of x is the same as f of a. So if you think about what the sketch is, it means that as you come in from the right-hand side, we're filled in on the right-hand side. Or we're filled in on the left-hand side, actually. It's kind of weird. So you see, as you trace with your right hand and you're going along that curve, in the end, we don't have an open circle, we have a filled-in point. That would be continuous from the right. Oh, do you guys want me to zoom out? All right, so continuous from the left is when I have limit as x goes to a from the left. So I have f of x equals f of a. So that's when we trace along the curve with our left hand and we get to a certain endpoint, and that endpoint is filled in. So it says, question, where is the function continuous from the right, continuous from the left? What type of discontinuities can be found on this graph? Okay. So let's first talk about where it's discontinuous in general. So discontinuous at x equals what, x equals what, x equals what. So at x equals -3, definitely, right? What type of discontinuity is that? It's a jump. All right, how about x equals negative, where else? -1. What type is that? Infinite, because there's a vertical asymptote. How about x equals 2? What's that? So we use the fancy term removable. All right, it's a hole. All right, now we want to decide if any of these are continuous from the left or continuous from the right. So as you went to this point right here, as you traced along the curve, did you trace from the right or the left? You traced from the right, and it became a filled-in point, right? That is continuous from the right. Because our limit as we approach from the right is the same as the filled-in point. All right, any others? No, the rest of them are not continuous from the right or from the left. Okay? All right. So it says, how should this be defined to remove the discontinuity at x equals 3? So in other words, what is the value of c that makes this a continuous extension for the function? So we need to first factor it and figure out where the hole is placed. So if I factor, I have x minus 3 and I have x plus 7. So my hole is at 3. What is the y value of that hole? So our simplified version is x plus 7, right? So what if you plug in 3 to that? You get 10, right? That is your continuous extension, 10. So if we were writing this as a piecewise function, what you would say is, oh, well, I have x squared plus 4x minus 21 over x minus 3 for all x value except for what x value? 3. And then we want to define the x value at 3 to be what y value? 10. That's how you do a continuous extension. So that fills in the hole. What we've done is we've made this equivalent to the line y equals x plus 7. We filled in the hole that was there. You're fine.
And that's how we write it for
You write it as a piecewise function.
Sorry, guys.
Yeah, so a lot of times you're going to have these problems that are going to say, find the values of a and b that make this continuous, right? So we're going to do something like that in a second. All right, so if you remember, we had limit laws. Yeah, so we talked about limit laws before, and limit laws worked with a product, with sums, with differences, with quotients, and so on. So the same thing applies for continuity, because continuity involves limits, right? So the definition of a continuous function is the limit as x goes to a of f of x is the same as f of a. Okay, so if we can use limit laws, then we can use this for continuity. So it says all parts of the theorem above follow from the 11 limit laws. So let's just do a quick proof. I know you guys love when I say proof in math class. So we're going to show that number 3 holds. So we're going to show that the product f times g works. Okay, so we want to show that the limit We want to show that the limit as x goes to a of f of x times g of x is the same as f of a times g of a. If we can show that, then we've shown it's continuous for the product. Does that make sense? Based on the definition of continuous. It's the same as plugging in the point. All right, so what we do is we say, well, we know that the limit as x goes to a of f of x times g of x, maybe I should do big parentheses, I'll do parentheses there too, is the same as the limit as x goes to a of f of x times the limit as x goes to a of g of x. Do you guys remember with limit laws why that's true? You can bring a limit into a product. So in our theorem, we said if f and g are continuous at a. So if f and g are continuous, then what is this and what is this? Yeah, so since f and g are continuous, we can say this is equal to f of a times g of a. And then we're done. Do you guys see what I'm saying? F of a times g of a. So the part that I circled in blue became f of a times g of a, based on the continuous. I probably should have written it at the beginning, but that's fine. All right, it's easy enough proof. So with all the limit laws, you can bring the limit in and you can say, well, since f is continuous, this is true. Since g is continuous, this is true. All right, so we've also previously talked about the direct substitution property. So as stated, for any polynomial or rational function where a was in the domain, it said that the limit as x goes to a of f of x was equal to f of a. Well, that's our definition of continuity, right? So it says, therefore, any polynomial is continuous everywhere, and any rational function is continuous wherever it's defined. So whatever doesn't give you a denominator of 0. So we're continuous as long as those numbers are in your domain, basically. Okay, so if there's something that's not in your domain, then it's probably not continuous there. There's something weird happening, like a hole, an asymptote, something. Okay, so for this, find the limit as x goes to 1. Do you see how you can just plug in 1? So I get 1 to the 4th minus 3 times 1 squared plus 5 all over 1 minus 5. So I get 1 minus 3 plus 5 all over negative 4. So what do we get? 6 minus 3 is 3, negative 3/4? All right, so negative 3/4. So it's continuous at 1 because it was the same as when we plugged in 1. These ones are easy. What's the limit as theta goes to 0 for cosine? We can plug in 0, right? Cosine of 0 is 1. Sine of 0 is 0. We like those. The whole test should be that kind of limit, shouldn't it? Wouldn't that be nice? It's just saying, like, you can plug if you can plug things in, then plug them in. It's just like the direct substitution thing. So it's continuous at 0 for both of those. All right, so the following functions are continuous at every number in their domain. So polynomial, rational, trig functions, radical functions. So trig functions, the domain is all real numbers, except for sine and cosine, right? So what about tangent, cotangent? Well, then you need to think about their domains. So number 1, so even if you have something funky like this, x to the 2000, yikes, is it continuous everywhere? Sure, it's a polynomial function, right? So it's continuous everywhere. You guys think you can recognize when something's continuous everywhere? Pretty easy. So there was nothing making it undefined. Okay, how about this one? Did I skip B? I feel like there should be a B. What was B?
f of x equals x squared minus 6x plus 9.
Just that?
All over x squared minus 16.
Okay. So what do we think for this one? Continuous everywhere except for what points? Continuous everywhere except 4 and negative 4. Exactly. So if you're lazy and you just want to write discontinuous, you can write DISC. at x equals 4 and negative 4. You can write it that way too. It's probably the fastest way of writing it. All right. Next up. Part C. What do we think with the denominators? Yeah, 1 and negative 1, right? Because the negative 1 comes from the second denominator. So it's not continuous at 1 and negative 1. It can't be negative. Good. So x has to be greater than or equal to 0. So let's think about that on a number line to help us. So we know that we have to be bigger than 0. We can't be negative 1, and we can't be 1. So the negative 1's not mattering because we already said it had to be bigger than 0. Greater than or equal to 0. So we have to skip over that 1. So we're going to say continuous on, and this is where I would do my interval notation. So I would do bracket 0 to 1, parenthesis, union 1 to infinity. So it's continuous in all those places. Okay, the most common question for continuity on the AP test is like number 2. So it says, what is a value for A that makes the piecewise function below continuous? Now technically what you should be saying is that the limit from the left is equal to the limit from the right. Right, that's what we need in order for the limit to exist. In order for it to be continuous, we need it to be equal to f of 2. Okay, I'm not super picky about this. The only times I'm picky about it is like on number 3. Well, of course, number 3 got cut off too.
So you just leave it at 2.
Oh, there it is. Number 3 where we had some kind of, where we needed to write a limit there. So I'll show you what I'm talking about with that.
Okay, so number 2 is just 2.
All right, so what we're going to do is we're going to plug in 2 for x, and we're going to set the right side equal to the left side. Because what we're talking about is we want our two sides not only to meet up, but we want for it to be filled in. All right, and the greater than or equal to thing is what's filling it in. So we want those two sides to equal. So I have 4a plus 3 equals 6 minus 5, so I get 1. I subtract the 3 over, so I get 4a equals negative 2. So a is equal to negative 1/2. That's the value that will make those two sides match up. Do you guys understand what I'm saying? Like, you want the right side and the left side, both curves go to the same value, and then it's going to be a filled in circle because of the greater than or equal to. All right. Number 3, I think I'm on the next page. So find values for a and b that make the piecewise function below continuous. Now it's a little bit harder, right? So now we want to set these two equal to each other for x equals 2, and we want these two equal to each other for an x value of 3. Do you understand how I'm getting that? Look at their domains. The first one said for x values less than 2. The second one said between 2 and 3. So it means as we approach 2, we want to go to the same value. And since we had, do we have a less than or equal to? Is this one less than or equal to? The top one? Yeah, that's going to fill it in, right? Do you guys see what I'm saying? So now, oops. So if you were writing it like plugging in 2, do you see what's bad about plugging in 2 into the top one?
It's undefined.
It's undefined, right? So it doesn't mean that there's not a point there, like as you get closer and closer to 2. But yeah, it's like, well, how do you find that? That's when you definitely need to write limit. So we're writing limit as x goes to 2. And you can say from the, would it be right or left? X values are less than or equal to 2 from the left. So limit as x goes to 2 of x squared minus 4 over x minus 2. We want that to equal to, and you can say limit as you go from the right, but I would just probably just plug it in for the other one, right? There's nothing wrong with plugging that in. You see that? So how do you think we're going to solve this limit thing? Yeah, factor. So I have the limit as x goes to 2 from the right, x plus 2, x minus 2, all over x minus 2. And then I get 4a minus 2b plus 3. Cancel your x minus 2's. So as you plug in 2 from the left, you get 4. So you want 4 to equal 4a minus 2b plus 3. So 1 equals 4a minus 2b. So I have an equation that has a and b. Do you guys see that we're going to have a second equation that has a and b? So now we're going to plug in 3 to the other one. Now this one's not one where we have like a denominator where it's undefined. I would just plug in 3 onto both of them. So you're just going to have 9a minus 3b plus 3 is equal to, so I plugged in 3 into the first. So I have 6 minus a plus b. So I set the middle equation equal to the bottom one. And I plugged into 3 for both of them. All right, so I'm going to get my a's and b's on one side, my numbers on the other side. So I'm going to have 10a minus 4b equals 3. You with me? You guys remember how to solve a system of equations?
6a minus
You guys look so enthusiastic right now. All right, we're going to multiply the top one. Let's multiply by negative 2. I'll go over here. So I get negative 2 equals negative 8a plus 4b. And then I'm adding it to 3 equals 10a minus 4b. So when I add straight down, I get 1 equals 2a. So a equals 1/2. And then when you find b, so plug it into one of the other ones. So 4 times 1/2 is 2. Subtract it over. So b equals 1/2 as well. Is that right? Can you guys check? 4 times 1/2 is 2 minus 2 times 1/2 is 1. 2 minus 1 is 1. Yep. So a is 1/2 and b is 1/2. Think you can handle that? Like I said, those are the most common AP questions for continuity. All right, and the last thing we have to talk about is the intermediate value theorem. So it says, suppose f is continuous on the closed interval a to b. So we draw a little sketch. So from a to b, we have a continuous function, so we can draw it without lifting our pencil. And then we have some y value. This is like the most crooked graph ever. All right, so y is equal to n. And we know that n is some number between our two heights, so f of a and f of b. So let's say f of a is here, and f of b is here. So we have a continuous function, so we have some kind of thing that's connecting those. Make sure it passes the vertical line test, though. Like that. Okay, then there has to be at least one number c, so at least one place where it's crossing y equals n.
Can there be more than one?
There could be more than one. So there is at least one number where that's true. So how do we use this? Usually if you see an AP question on the intermediate value theorem, it has to do with zeros. So if you know that you have a and b as our interval, and let's say f of a is here and f of b is here, and we have a continuous function that joins them, then there has to be a 0, an x-intercept between them. Okay? So you'll see that a lot with the intermediate value theorem. So there has to be a place, so our blank is f of c is equal to n. Usually used for zeros. So zeros are x-intercepts. All right, do you guys remember doing this in pre-calc? We did it. I always like teaching consecutive classes because people are like, I don't remember this. We never learned this. I'm like, yeah, we did because I taught it to you. So we did this. All right, so the IVT pops up often. You definitely needed to know this one. So put a star next to it, make a flashcard. So it says, show that there is a root of the equation 3x to the fourth minus 5x squared plus x minus 2 equals 0 on the interval -2 to -1. All right, so the first thing we have to do is we have to define a function because I don't want to talk about f of -2 and f of -1 without ever saying that I have a function f of x. Do you guys see how there's no f of x in our original? So we have to say let f of x equal 3x to the fourth minus 5x squared plus x minus 2. Is that a continuous function? There's never a place where it's undefined, right? A denominator or anything, square roots. So yeah, f is continuous everywhere. So we can draw it without lifting a pencil. So now we want to find f of -2 and f of -1. We want to find our a and our b values from our interval. So f of a and f of b. All right, so f of -2. 3 times -2 to the 4th minus 5 times -2 squared plus -2 minus 2. Let's see, 48 minus 20 minus 4. 24?
Yep.
All right, and then f of -1, 3 times -1 to the 4th minus 5 times -1 squared plus -1 minus 2. So 3 minus 5 minus 3, -5. We're trying to find the root. That is the same as an x-intercept or a 0. You could see any of those words, root, x-intercept, 0. All means the same thing. So we just showed that f of -2 was bigger than 0 and f of -2, or f of -1 was less than 0. You don't need to do a little rough sketch, but basically here's what's going on. We got f of -2 is way up here at 24. And f of -1 is way down here at -5. And if we have a continuous function, don't we have to connect those somehow? So if we have to connect them somehow, it has to cross, we have to cross the x-axis between -2 and -1. So therefore, there is a root on -2 to -1 by the IVT. So if you are going to get points on your test for doing this, I need to see 3 things. I need to see the let f of x equals something. I need to see that f is continuous. And I need to see that 1 is positive and 1 is negative. Those are the most important parts. All right, so it says use the IVT to verify that f of x equals x squared minus 7 has a 0 on the interval. Is this the last problem? I think it is. Oh, okay. Maybe we'll pause. You guys need to go on your break. We'll pause. So it says use the IVT to verify that f of x equals x squared minus 7 has a 0 on the interval 2 to 3. So we have our f of x already, so this time we don't need to say let f of x equal whatever. We already have it. We know that f is continuous, so we write that. If you don't do that on your test, I will count you off. All right, we find f of 2, and we want to find f of 3. So f of 2 is 2 squared minus 7, which is -3. And f of 3 is 3 squared minus 7, which is 2. 1 is less than 0 and 1 is greater than 0, so that's good. So we know that there has to be a 0 on that interval. All right, so we're using the method of bisections. In other words, we're going to keep having the interval until we get the size that we want. Do you guys remember doing this? No. Okay. So we have the interval 2 to 3, and we got that 2 gave us a positive number. Or no, wait, a negative number, right? And 3 gave us a positive number. So there has to be something between the two. So let's make it even smaller. Let's say between 2.5 and 3. And you can use your calculator to help you. So if you do 2.5 squared minus 4 minus 7, sorry. I was setting up a table. All right, 2.5 squared minus 7.
-0.75.
Yeah, -0.75.
By the way, I haven't found my calculator.
I know. And then so that's negative. So now where's it between? Between 2.5 and 3, right? So now we would do half of that, 2.75. So when I do 2.75, this is why I had it set up in my table, I get 0.5625. That is greater than 0, so that's positive. So now what are we between?
2.65.
2.5 and 2.75. Is that an interval of length 1/8 yet?
No.
No, right now our interval is 0.25, right? 1/4. So we go one more time. So we do 2.625. If you did not know how to do that, I would do 2.5 plus 2.75 divided by 2. Find the average of the two, right? Directly between them. So when you do 2.625, you get a negative number, so negative 0.109 something, which is less than 0. So it's between the interval, or it's on the interval. I'm going to do parentheses, not brackets. Why am I choosing to do parentheses instead of brackets?
Because you don't actually have points there.
Yeah, those aren't zeros, right? They didn't exactly equal 0 at those points, so I can say it's between those two numbers. All right, so it's on the interval 2.625 to 2.75, and that is an interval of length 1/8. Does that make sense? So you have it.
Just has to equal less than or equal 1/8.
Yeah.
Is it alright if it is less than 1/8?
Oh, because it's not exactly 1/8. Oh, you were so particular. Yeah, that's true. It's okay if it's not exactly.
So what do you mean? 0.125 is 1/8.
I know what he's saying because you don't include the endpoints. It's kind of less than that, right? Tricky. All right, is there any real number exactly 1 less than its cube? Okay, I've asked questions like this in the test before, and people just have no idea what I'm asking when I say this. Okay, so is there any real number exactly 1 less than its cube? So is there an x value that is 1 less than x cubed? So x is equal to x cubed minus 1. So that's the equation we're solving. So if I get everything on one side, I have x cubed minus x minus 1 is equal to 0. So we're going to use the intermediate value theorem. We're going to let our f of x equal x cubed minus x minus 1, and we're going to find a 0, or show that there has to be a 0. Jordan, you with me? It's hard once I'm staring at you guys as I'm writing notes, right? So f is continuous. So let's try some values. So what if we try f of 0? We get negative 1, right? That's less than 0. What if I try f of 1 though? What's f of 1? It's also negative 1. That's less than 0. That's not helping me. I don't have one that's above and one that's below. Is this graph just a straight line at negative 1? No, we know it's not a straight line at negative 1. We know every single value doesn't give negative 1, right? So let's try f of, I don't know, what else do you want to try?
2.
F of 2. 2 cubed minus 2 minus 1 is 8 minus 3. So we get 5. That's greater than 0. So we know that there has to be a 0 between 1 and 2. Does that make sense? So therefore, there must be a 0 on 1 to 2 by the IVT. Intermediate value theorem. Done. All right, does that make sense? Do you guys understand that? All right, so we're going to stop there.
I'm down to try not to find